I've gone live, I don't know how many times, not gonna lie, today. Probably 3. This is the 3rd time. The first time was for 4 hours. Second time was for 3 hours. That's 7. Let's see how long this is gonna be. So we are doing the circuits lab. It is 9:12, and we need to turn it in by 11:12. So we got 2 hours. Not. It's due at midnight, but I'm turning it in at like 11, whenever, just because. I do. I pull up to the. I'm gonna send the link to this to my girlfriend because why not? But I don't know how to share it. Stream settings, stream URL, copy. What if I just. What if I paste that? I'll put up to the after party. That's weird. I don't know. I don't know how to share this. Oh, there it is. You know what? I don't. Okay, I just sent the link to my girlfriend, but then I changed my mind, so I told her to ignore it. So, yeah, let's see. The delay is pretty bad. I'm not gonna lie. Or did it freeze? No, it didn't freeze. And it still says we're live for 3 minutes. We've dropped barely any frames. So anyway, let's get started with this crud, bro. Let's just get with it. So, I got my coffee. My phone screen ain't working right. Now it's going. Oh, there we go. I got it. Alright, so this is my phone. And my phone streams to my computer that streams to the world. And so then I angle it like this, and now, haha. Okay, cool. Let's go. We've wasted 3 minutes already. Alright, we're in a rush. I'm upside down. What? Why? Flip. Okay, there we go. I don't know why it keeps doing that. It wasn't doing that earlier. But once it's set up, it's usually just so you can leave it there. I might need to plug it into the computer, but we'll see. So, let's get started. The stream delay is kind of slow. But anyway. Why do I stream? If you're watching this, Grace. I stream video games sometimes, so I decided I was gonna stream this on a dud channel. This is my fake. This is just my dud channel. That's all. But anyway, so let's go. First, we need to describe the lab. Basically, we can restate this. So I've got my Word document up, and I've also got my other lab report pulled up for formatting purposes, because I don't like to remember too much. So, hold on. In this lab, we will apply a, what am I doing? Type. Thank you. This thing was like supersonic speed earlier, but now it's just slow. In this experiment, we will apply a pulse waveform to the RC circuit to analyze the transient response of this. So we will apply a pulse. I wasn't paying attention. Waveform to a RC circuit, which, what does RC circuit stand for? RC circuit. It's usually just a circuit with a resistor and a capacitor. I know that, but like I wondered if there was a special term for it. So I'll just put a circuit with a resistor and a capacitor. My other stream, I was streaming earlier for like 4 or 5, maybe 6 hours, and what happened was YouTube shut it down because I was playing copywritten music. So I got my Google Home in the back playing some softer music, and it's just like focus music, you know, because if I listen to too much music, I am going to, you know, lose out. If I play too much music, I'm gonna like get claimed or whatever. But I don't understand. I'm not making money off of this, so why does it matter? We will apply a pulse waveform on RC circuit to analyze the transient response of the circuit. The pulse width relative So whenever a voltage is applied to an RC circuit, the voltage and then I can format this. What is it? Oh. Assume we have a step function or constant DC voltage applied to a series RC circuit starting at t equals 0. The capacitor would start to charge towards voltage V. Okay, let's just, the capacitor, capacitor will charge up to the applied voltage value given by the formula. Now we can get rid of these obnoxious spaces, where V sub C is equal to the voltage across the capacitor, and V is the applied voltage, and I don't know how to do tau, so I'm going to have to copy it and then bring it down. And tau is the time constant. Is the so-called time constant. And we should put it in quotes. The following figure shows a graph to visualize the capacitor charging. Note that the capacitor is the capacitor reaches 63% of the applied voltage. I'll just say of the voltage source when just time is equal to tau. Okay, there we go. Period. So now what we can do is insert this little graph, and the graph will help make it make sense. Okay, cool. We're still going. Basically, this right here is the main computer screen. Now, the whole system is one computer, actually, except for the laptop over there. But this one computer screen, camera is here, obviously. I'm pointing to it. The microphone plugs in way over here, which then the headset, microphone, whatever, and the mouse and the keyboard all plug in down here. A wire goes down to the keyboard, and I've got another monitor way over there that you can't see because I'm pointing off camera, and that monitor has my stream software output that's displaying what the stream is outputting, and it shows me how long I've been going, as well as the camera output to make sure it's not frozen. And then the camera also, or the whole live stream is being monitored on that laptop down right over there. You can see it right there. And so that laptop is making sure that, like, so that's like the final product, and then each of these are the stages of it. And for right now, since I'm rendering a lot of video, I'm going to make sure my processor isn't too hot. And it's pretty average, I'd say. It's hotter than I'd like it to be, but my room is a literal... Oh, my room is a heat trap, so I'm going to go turn the AC on real quick. I need as much airflow as possible, and then I need to make sure my mic doesn't mute through here. Okay, we're back on it. So now I need to take a screenshot of this. I like using Gyazo because I can just literally like click and drag like a Mac. And then, I mean, you know, it's not as good as a Mac, obviously. But then I think it's better because then you can just like copy the image. You don't have to save it to your hard drive. It goes up to somewhere else. And then I can just paste it in. And then let me just resize it and make sure it wraps tight, not in line with the text. So I can like, I can do something like this. And I can say figure 1. And now for this, I'll just say capacitor charging for series RC circuit to a step input with an axis normalized by tau. Figure 1, so capacitor charging for a series RC circuit. Now, a series RC circuit is just where the resistor and the capacitor are in series, not parallel or something like that. Bro, these Frappuccinos from Starbucks, they're so good, but the lids suck. Like, make better lids. They don't screw on. Like, if I tumped it upside down, it'd spill. It's ridiculous. It's not what thing is for. I think I put an extra space in here because I am just hyped up on caffeine right now and doing my work. It's 9:27, not bad. Okay, so the time constant is a measure of time required for certain changes in voltages and currents in RC and RL circuits. So, okay, so I'm gonna include this, a measure of time, the time constant is a measure of time for the circuit in figure, for our circuit in this lab, tau is equal to RC. The circuit we will be, wait, let me just, okay, yeah. So I'll do it something like this. Okay, so now, oh, this is a picture. When an RC, when a capacitor is charged fully to, when the time reaches, when t equals 5, oops, how do I copy tau? It's right here. When the time reaches, when t equals 5 tau, the capacitor is, basically, I don't want to use that, but, effectively, maybe. Let's see. The currents have reached their final values, and the capacitor is in the steady state response. The currents and voltages have reached their final values, period. This is called the steady state response. And then there's a hyphen there. So now we have to talk about discharging. Then we're going to put a picture of the circuit in there. Then we're going to explain how we're poking voltages in there. And then we're going to explain my results of the experiment. And then we're going to answer the questions and we're done. It's not too bad. Not bad at all. And we're only at 200 words, which is perfect. But up to the after party. Why is it 11? Pop that up to 12, and then move the figure speeches down to 11. Perfect. Ooh, now my typography is good. I like good typography. After, or let's just say, when the capacitor in the RC circuit is reaches its final value, and the voltage source is cut off, the capacitor will discharge according to the formula. And now we just do a little gaiazo, and we're going to very carefully select this. But see, that didn't work, so let's just close out. We don't have to worry about that one because I missed that RC, so I have to clip it as high as I can. I'm trying to get it as close as possible so I can just like copy this and pretend it's text, and so then I can do something like that, and then I can also make this tight wrapping and then make it tiny, or make it about the same. There we go. Ha ha Let's go ahead and get this this in here, because this is helpful. You can see how it discharges. Ooh, excuse me, I burped. Also, I wonder if I got any text messages. And, let's see. Nope. No texts. Good. I've been, emailing a bunch of people today with different things, and I don't want to miss a response. Okay, so this one's going to be a tight wrapping, and then this little anchor point's going to go way up here, so I don't have to worry about it. And now, this is going to be moved down to 11, and we're going to say figure 2, capacitor discharging for the RC circuit. And then we can go up to 12. And now what we're going to do, so there's the in this experiment we will use square wave pulses as the inputs, instead of DC of a DC voltage. A pulse is a voltage or current that changes from one level to another and back again, or whatever. If a waveform's height time equals its low time as in the figure, it's called a squared wave. The length of each cycle of a pulse. So the length of each cycle of a pulse is a period. T. The inverse of the period, 1 over T, is the frequency, F. Oh, the number of periods in 1 second is called the frequency. Okay, never mind. the number of periods in a 1 second is the frequency. Okay. The pulse width, TP, of an ideal square wave is equal to half the time period. The relationship between the pulse width and the frequency. Why is this? Whoa, cancel. Why is this 14-point font? F is equal to 1 divided by 2TP. Okay, this is the last thing that I have to enter before we get into the thingamabobber. We can also wrap this text tight. Oh, it went all the way up here and it's messing with my vibe. But I guess I could just, like, pop it here. And then just say that this is figure 3. Yeah, figure 3. A square pulse voltage. A square pulse voltage. Red or pink. And capacitor voltage. Red. Oh, adding that one little parentheses messed it up. But what if I bring it down to 11? And okay, I'll just leave that there and then go to the end and then hit enter, and now we're on a fresh new page. By the way, we need page numbers before I forget. Add page numbers at the bottom right. Close header and footer. Okay, cool. Okay. Or yeah, let's do that. Let's do procedure. And this has to be 12-point font. The circuit, we will, the circuit that we will set up is shown in the figure below. The resistor value will be 2 kilo ohms, and the capacitor will be 1. I need micro mu. I need a mu. Give me a mu. Can I get a mu? Mu. Copy. Paste. Copy and paste easily at Emoji Mall. Copy and paste. Where is it? That's not it. Alright, well, I copied it. Hey, there it is. 1 microfarad. From this, we can calculate the time constant since tau is equal to RC. 2,000 times 1, let's do parentheses, 1 times 10 to the minus, what is micro? 10 to the minus 9, right? No, minus 6. Minus 9 is nano, which is equal to, what is that? 2,000 times 1, oops, times 1 times 10 to the minus 6. 0.002 seconds. 0.002 seconds. Or tens, hundreds, thousands to ms. 2 milliseconds. That's all that is. All this has to be font size 12. Okay, cool. Why is it? No, it's just 2 milliseconds. It's not misses. Or miss, I should say. Are we still rolling? We still rolling in the dough. Heck yeah. I go. I need a break. I've been typing a lot. Hey. But we can take breaks when this assignment is finished. That's how it works. That's how we do it. Okay. So, the time constant is automatically calculated to be that. We will measure the voltages across the capacitor of our circuit and try to measure the time constant To do so, we will use the Analog Discoveries voltmeter and oscilloscope and oscilloscope. How is that? OSCILLO, yeah. And waveform generator to generate the input pulses. Okay, generator. Cool. Now, the pictures are on my phone, unfortunately. And so I'm going to have to do a little bit of finagling. I need a break. But we'll take a screenshot of this. So, let's do it like this. Let's give that a go. A little bit of a screenshot. Copy that image. And then paste it. And this is going to be figure 4. Well, hang on. So now we got to wrap it tight. And now I can say Figure 4. RC circuit. And then, well, let's back up. Oh, there we go. That's better. That's right on the money. Okay, so now what we need is my picture that I took of the breadboard earlier. I think I still have it on my phone, which means there ain't gonna be a there ain't gonna be a camera for a little bit. So let me just there we go. Got it paused. I had to make sure it paused in a good location. You know how I am. Okay, so now let me delete that. So the only picture that I have is actually wrong. It's upside down and it doesn't make any sense. So I'm gonna have to just first take a picture of the circuit on its own. So yeah, that's what's gonna happen first. But I'm still here, I'm still talking. And so now I'm going to go ahead and take that out. Okay. What did it say? Oh, my iPhone just disconnected from the thing. Okay, cool. So I have it connected in. And now I can actually reconnect the iPhone like this. Let's go back to Ivy Cam. Let's wait till it pops up. There we go. We got it back. Alright, good. Let's flip it around. So here's my little circuit. That black thing's the capacitor, and then these two resistors are in series to make... These are each 1,000, so put them in series and you get 2,000, because 2 1,000s. So now what we need is... First we're going to need a... my screen went black for some unknown reason. What the heck? My screen black. Now I have to disconnect it and reconnect it. Doing this. There we go. I don't know why my screen keeps going black. And it's like... Okay, but anyway. So, what we're going to need is, up at the top, this resistor. This is where the voltage source is. So it's like, imagine a battery. My screen went black again, but I think it's still filming. Yeah, it's still going, but now it's just freaking upside down. Okay, but anyway. I don't know why it's... Oh, it was an advertisement. They put ads on this thing. That's so dumb. But anyway, okay. So, like, imagine a battery right here with the positive side here, negative side there. So that's, like, the thing. And then these resistors are in series. So there's the battery, that weird squiggle thing, because it's going to be a square wave intake. There's our resistors, and then our capacitors right next to it. And then this little wire is connecting towards the battery just because... I say battery, but it's really just all these wires, and it's just applying a voltage kind of like a battery, but it's not. So, anyway, the first thing that we need to do is we need to get this thing all set up. Sorry, I'm kind of trying to be careful here, because there's some delicate pieces that Yep, okay, I got them. Okay, so anyway, this little yellow wire, it's going to... This yellow wire, this is going to provide the waveform. That's sending the square wave in there. And then this little black wire, wherever it might be. There's 2 black wires, but there's one that's right. Okay, there's a big clump of wires right here. Sorry, I'm not even showing it to you. But this clump of wires, that black wire in there, that's the ground wire. Let me just instead set the phone up like, or here, let's just flip it around and then do it like that. It's going to be kind of wonky, but that's okay. So this little black wire, wherever it, yeah, that wire has to go here. Oh, I messed this up. That one goes there. So the black wire goes there, and then there's an orange wire, and the orange wire is measuring the voltage across the whole voltage source. So the orange wire is the first channel of the oscilloscope that's going to show us our square wave. You'll see what that means in a second. It's confusing right now. And then there's a blue wire that's just measuring the voltage across the capacitor. So the blue wire is measuring that, that squiggly line graph that I showed earlier. And so there, I've got it all wired up, and now I carefully just set this at the back of my table and hope my mouse doesn't hit it. And so there we go. Now it's all set up, and now I can set this bad boy back up right there. And let's make sure I'm still not frozen. No, I'm not frozen. I'm good. I got ultra low latency turned on my stream, but for some reason it's like a literally 20 30 seconds, maybe even more behind. And that's okay, but anyway, so now I need to take a picture of that. I forgot. So let me take a picture, and then I need to actually do something else. Okay, I got the picture. It looks okay. I'm gonna crop it just to, there we go. And now I'm going to airdrop these to my computer. If it'll pop up. Me computer ain't popping up. Me MacBook Pro ain't popping up. Oh, it popped up now. Very good. It goes boo, 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 boo. Let's refresh this page. Why not? Alright, so I got them there. Now I'm going to exit out. I think I can just delete these, not gonna lie. If I need to get them back, I'll go recently deleted. Not too bad. Now I'll go back to Ivy Cam, make sure I'm in. Let's get a clear connection. Yeah, that's good. Lots of good Wi-Fi signals. So now, here I am. And, see, I got this thing on ultra low latency. But, look, see, it still shows the frozen screen. Deleted, not too bad. Now I'll go back to Ivy Cam. It's kind of slow. But anyway, now I'm going to go to OneDrive. I have it installed on my computer, but it's a little buggy. But let's just try it in the computer. Why not? So I'll go to OneDrive, Circuits One Labs, Lab 7, and then just dump those in there. And we'll see if they are uploading. And OneDrive does say that they are uploading, and it will tell me how far they're going. Pretty good. Look at my output. I'm going at half a megabyte a second for my internet speed, which means streaming takes up a lot of internet bandwidth. But that's it. Sweet. So now they are up to date. They're in there. I'm going to close that and leave the live stream up, and now I can come back here. Oops, I didn't mean to take a picture. Gosh darn it. It put a picture on my desktop. That's kind of cool, not going to lie, though. Like, I can just take pictures and have them instant. Like, that's how I can. That's how I should have done it. That's how I should have taken the. I went all to that effort because AirDrop is way fast and, and it's higher quality than this camera. But I mean, like, it would be like an instant thing. Anyway, so now I come to my computer and there they are. So I can download these by trying to open them. And now they open up, and now that they're downloaded, I'm going to close out. And now I'm just going to add, so the first one, sorry, I thought there was something hard in my coffee. By the way, this is the formula for a 100 on your circuits labs. 100 on the circuits lab. 100 on the circuits lab. Let's get this out of here. It's bad for the aesthetics. I just like this. I like that aesthetic. Ooh, I am hyper. But that is good, because I could channel my hyper energy into doing this crap. So, it's not crap, though. It is definitely not crap. So now, I'm going to make figure 5 and 6. These bad boys. They put them in sideways. But that's okay. That's how it works. Where did they go? Oh, they went like this. Oh, this one's bad photo. It's orange. But I really don't care, not gonna lie. Why is it over here? These can be way smaller. Like, literally, that size. Like, it might not even be worth it to have that first picture. But it's okay. Microsoft Word and inserting photos is, like, the most nightmarish thing. And we're gonna do tight. Where did it go? Oh, it went down here. And we can also do tight wrapping. Tight. There we go. Now they're stacked. But see, this is how you should be able to manipulate photos. Okay, he's gonna just... Professor is just gonna... Oh, and so see, look, with this whole anchor point thing, we can drag it up here. And then with this anchor point, we can drag it up here. And then now we don't have to worry about doing any of that. So now I've got calibrated foot. So figure... Oops. No, whoa. Figure 5. Breadboard configuration. And then... Figure 6. Analog discovery configuration. Yellow and black are the wave gen wires. Yellow and black will generate the waveform as the voltage input. Orange is oscilloscope channel 1. Blue is channel 2. Okay, cool. And then we can just enter that a couple times to make it sound or look good. And now we can go on to page 3. And then up our font size, make it not bold. We are ready to talk. And then tab over to start a new paragraph. So now that we've got that set up, we just need the other thing. Oops, that's the other lab. Let's go here. Nope. Let's go to the internet. Where is Google Chrome? Why is my computer so laggy? It's probably because I keep going back and forth to this one, and it has a lot of photos on it. Joe with the B.I. Joe with the B.I. Bo with the B.I. Bo. Up, uppity. Okay, so now we just need to explain. Okay, so now for this part, I have screenshots. I have receipts. So the first receipt is this one. right here. Copy image. Paste image. We'll do like that. And then gotta format it right. So this one's gonna be figure what? Figure 7. Waveform generator window. Let's go ahead and just, there we go. Figure 7 waveform generator window. Square wave voltage in. And now we're going to do this. And we're going to say, we're just going to explain this part. Here the input voltage will toggle between 0 volts and 4 volts with a frequency of 50 hertz. This is because if we select the such as the pulse width, because setting the frequency to the because choosing the frequency such that the pulse width TP. No, I don't want to print right now. Chill out, bruh. TP. Nope. TP is equal to 5 tau. Gotta go up here and copy my tau. Where's my tau? Here's my tau. Calibre 12. Good, good, good. If we set such as the pulse width TP is equal to 5 tau, then the capacitor can reach, let's just say, fully charge by and discharge during one pulse during each pulse cycle. Since we calculated tau equals 2 milliseconds, that means that TP is equal to 5 times 2, so 10 milliseconds. Let's just put this on a new line to make it better. That means TP is equal to 10 milliseconds. And since the frequency, where was that equation? It was up here. Is equal to 1 over 2 TP. Haha. Is equal to 1 over 2 TP. That sets, wait, what? 10 milliseconds times 2 is 20 milliseconds, and then 1 over 20 milliseconds, 1 divided by 20 is 0.05, but since it's milliseconds, it's like 0.002, which is 500, but it was 2 times 20 times 10 to the negative 6, so it's just one of those. So that's where that 50 comes from. Okay, since the frequency, and since frequency equals 1 over 2p, 50 hertz is the desired frequency. Okay, for procedure 1, you need to measure and record the time constant output waveform. Again, the pulse width is exactly 5 tau. It should be able to just fully charge and discharge. So we can use the output waveform and then measure our time constant using voltages. We can measure the time constant by looking at the output plot of the 2 oscilloscope channels. 2 cursors will be used to find the time where the capacitor's voltage equals 0. Capacitor's voltage V sub C is equal to 0, and then when V sub C is equal to 0.67 V, right? Is at 0% of the maximum, and the 2 cursors will be used to find the time where the capacitor's voltage V sub C is at 0% maximum, and when it is at 63% maximum. I don't really know why that is. Since maximum is 4 volts, 63% of 4 equals 2.52 volts. Okay. So now we can go ahead and pull up I did it wrong. So see, in my cursors, they aren't at the right place, which is okay. I did this earlier, but let's just redo it again. So we've got waveforms open, and we got 50 hertz, 20 milliseconds period, amplitude's 2 volts, offsets 2, so it's going from 4 to 0, which is good. There's no phase, run. And now for scope 1, we're going to do a single shot, and we're also going to kill the cursors. How do I X cursors clear? Yes. X cursors. Okay, cool. So now we can see that it's getting up to the top and it's discharging. So let's do a single, because so what happens there, let me run it, and you'll see it just wiggles, and so it's hard to get. Let's just do single, and then it'll just give us a good solid snapshot of what's going on. So now I'm going to take X cursors and I'm going to add 2 of them, and then the first one is going to go right here. I wonder if I can zoom in on it. Yeah, like right there. And then the second one is going to go, so channel 2 is the whatchamacallit. How do I zoom back out? Magnifying glass fit. Okay. There we go. And now this one, we have to find when this blue line, when the capacitor's voltage is 67% of the top voltage. So you can see C2 is right there. So that 67% mark was 2.58. I think I got it. 2.52, dang it. Just zoom in a little more. There we go. And then fit it. Okay, so now I can hide this. Okay, so now we can see that on this one, it's pretty close to 0, so that's good. And now we're just going to do a screenshot of this whole entire window. Just like that. Ooh, that's a good screenshot right there. Yeehaw. So see, that's what the math showed. You know, it goes, that's the discharging. So the yellow line is your input voltage, and as soon as you kill the voltage out of the whole circuit, the capacitor actually decreases the whole voltage across itself. So you can kind of like easily fade out. You know what I mean? You can easily fade out a circuit like that if you ever needed to for whatever reason. You know, if you have some kind of component that can't just be cut off instantly, or if you like, I don't know, like what I'm thinking is, what if you had like a computer and the power cuts out and the computer needs to like save itself? You can have like a fat capacitor to like store up a bunch of charge, so while the computer's on, it's just charged up, and then as soon as the power gets cut, well, they're still charging the capacitor to save all of the files. I don't know if that's actually how it works. I'm excited to learn about things like that, and maybe I can, you know, maybe that's like, maybe I just came up with something, but I'm sure that's how something out in the world works, you know? That's how somebody's done it. So anyway, now that that's all fine and dandy, let's copy this image and then paste it into Word. Let's do with text wrapping. Like that. And then there we go. It won't let me go enter. Oh, there it goes. But now this little anchor. Where did it go? Oh no. It came all the way up here. No. We're going to do inline with text. And then bring it all the way down to the bottom. There we go. And now we're just going to go enter. And then make it 11-point font. And then type it in. Figure what? What? Oh. My chin just popped. Making funny noises. What figure is this? What figure? It's number 8. Figure 8. Oscilloscope window with cursors on VC equals 0 volts and VC equals 2.5 2 volts, 0.63 of max. Alright, there we are, and now we can just oscilloscope and then make it less bold, jump it up 1, and so from the okay, so the first cursor is centered, is placed at t equals 2.4632 milliseconds, and the second cursor is placed at 3.3895 milliseconds. So the time elapsed between the two is 3.3895 minus 2.4632. Which is equal to whatever that's equal to. Let's pop it into our calculator, or Google calculator. It's going to say 0.09263, so 0.9263 milliseconds. So that's how long it took for the thing to go from, that should be, that's wrong. It should be the time constant. Why ain't it the time constant? Wait, 0.63 times 4, 2.52. Okay, I thought I did that right. But why is it, what is it like that? That's really off. That should be 2 milliseconds. Very close. Maybe it's right there. 2.467, 3.3895. That's going to give us a little bit of a better, see, that's probably going to give us a little bit of a better look at it, but I don't know why. I don't know why it's doing that. Like, bruv, what intonation? Is this capacitor alright? You alright, little capacitor? I don't know. Oh, crikey. How do I, why can't, could I just, like, highlight this and then paste in its place? Okay, I can. Did it change anything? Not too bad. And now, what I can do is I can say 2.4617 and then 3.3895, and now that's barely going to make a frickin' difference, but it might be enough to, I don't know. I don't know what I did wrong. I mean, I didn't do anything wrong. As far as I know, I'm following this to the T. You know, you can read it for yourself if you want. But it must just be something weird with the capacitor. I don't know. Because look at, his capacitor is fat, and my capacitor is tiny. So I don't know. Maybe that's the difference. But my capacitor says 1 microfarad. 1 MF. Not milli, but the mu. But you know, it's 1 micro. I'm just messing with I'm just messing with myself here. But anyway, that's just crazy. So let's copy this. Let's paste it into here, and it's going to be 0.9278. That's closer, but by not much. Although, or whatever, I'm just going to roll with it, because it's 1022. Although this should have been close to the 2 milliseconds time constant that we calculated. I use we in this because I don't like to use I guess. But I guess I could switch we to I. But when it's we, the blame is less on me and more on a group of people. What was I going to say? Time constant that although we should have been close to 2 milliseconds that we calculated. The measured value, or the measured time constant is likely just... Did I specify that, like, and when it's at 63% of the maximum, the time it takes for this the time it takes for this to what? The time it takes for the capacitor to charge up to 63% max is the value of the time. Is the time is where t equals tau. So to find tau, we just measure that time. Is likely the measured time constant is skewed likely due to tolerances, and what else did he say? Due to tolerances of each component and the analog discovery. Now we will increase the frequency to 200 hertz. We will hertz and observe the voltages across the capacitor again. So I think I increased it to 200 hertz and made a screenshot, but let's just crank it up a notch and do single. And then we're going to clear those cursors. And pull up Gyazo and screenshot this. Copy. Paste. Again, this is a fat photo, but we don't need too much. Figure what? 9? Oscilloscope window with 200 hertz frequency. So it's gotta be right there. And then down here. Okay, good. That's good text. When the frequency is not, I believe if the frequency was an order of magnitude or whatever, you could say, or I don't know, when the frequency is not when the frequency is not the right length the capacitor has does not have enough time to charge fully and discharge fully in one pulse cycle, because the voltage, the input voltage, is switching on and off faster than the 5 tau. Where did I put my tau? The 5 tau that is needed for the capacitor to fully charge or discharge. Okay, so that's that one. Can you reliably calculate the value of the time constant? Although it is possible to calculate the value of the time constant even if the capacitor cannot fully charge. And before I type any more, let me work on that, because first of all, we need to kind of offset this. We need to bring it down to like minus 1.5 or something. I'm trying to get this, yeah, perfect. I'm trying to get it to where the bottoms match up, because for some reason it's off. That's probably why I was kind of off, but we'll do X cursors. We'll add 2 of them and hide this window. So now for like the charging, if I put this first one at 0, and then I can get this one to that 2.52 mark. Zoom in a little bit. Ooh, yeah. It's good enough. Oh, and then see, this one I can get lined up better. It's just rough, though. It's going to be the same. And so now we're going from however far, negative 952 microseconds. So negative 374. Or wait, where's the first one is negative 952, and we got to do, so negative 374.54 minus negative 952.54. That's going to be 578 microseconds. So from milliseconds, that's like how many microseconds in a millisecond? 1 millisecond is, so this is like half a millisecond. So I actually don't believe that. I'm just not going to put an example, but it should still be possible to measure the time constant if you measure the time it takes the capacitor to get from 0% max to 63% max, as long as the capacitor, as long as the V sub C can reach that voltage in the within a pulse cycle. Questions for the lab report. Using an ohm meter, measure the exact value of resistance R. In the above experiments, 2K resistance may measure more or less due to tolerance. Optimally, if your DMM has a capacitance meter, measure the actual value of the capacitance. Recalculate the time constant tau. Okay, so, lastly, I will measure the resistance. I will measure the exact value of the resistance using an ohm meter, or a digital multimeter. Let me see if mine has capacitance mode. I don't think it does. Let me make sure, because I don't know what the symbol would be. I mean, I think I know, but I don't know, because I don't know if I have it or not. Capacitance multimeter. What does it look like? This one looks like it might have something. Images. Is this capacitance mode? Tell me what capacitance mode looks like. I want to know if I'm missing something. Because there is a weird mode that I don't know what it is. But, it's just... What is a... Ooh. Well, I guess I could just test it. It's not like I want to hurt anything. So, of resistance and capacitance using a digital multimeter. Oh, I need to save this. Control-Shift-S. No, wait. File. Save as. Who texted me? I don't know who that was. OneDrive, Circuits 1 Labs, Lab 7, Lab 07 report. I'm having anxiety that my computer's gonna crash before it saves. Whew. So now that it's saved, I am relieved. Let me go see who texted me real quick. I'll do it on this computer because it's more private. And it was, oh my gosh! My girlfriend's cousin's dog just threw up on my girlfriend because she's over at her cousin's house. Poor girl. The dog's name is Dobby Loco Weedo, or sometimes just Dobby Loco Weed. We call him Weedo. I don't know. The names is, I don't know where they came from. And he'll respond to any word that starts with a D, so we just call him any D word, like, you know, dumpling was one of them that he responded to. He likes diarrhea because he always has diarrhea. And then, I don't know, he just eats everything that he, like, sees. And he's really, like, a small little chihuahua-looking dog or something. Or he's not a chihuahua. I don't know what breed he is. He's like a, I don't know. But anyway, he's, the exact, I need to measure the exact value of the resistance and capacitance using a digital multimeter. And recalculate the time constant. That's what I have to type. And recalculate the time constant. The experiment assumed the resistance... The experiment calculated the time constant, assuming the resistance was 2000 or 2k ohms, but due to tolerance they might be slightly What if it's because I put my resistors in like parallel or something? But anyway, now I can't measure this. Well, I can measure them, but I want to take pictures of the digital multimeter so that way, like, I don't know, it's easier to like see. So I'm gonna do the first part here because I think there is a capacitor mode. But for resistance, I'm just going to put the positive probe on one side and then the negative probe on another. And that's 1 kilo ohm. And then that's exactly 1. 1 point. Oh no. Let me answer this. Yo. What happened? Are you actually sick? Alright.
I tried that frosted animal cookie blizzard.
Whoa, is it any good from Dairy Queen?
It wasn't as good as I thought it was gonna be.
Oh,
So
that seems like everything from DQ, not gonna lie. Okay, so anyway, here's the room tour. There is a really messy desk.
show Madison your cool light.
Oh yeah, there's the lights. They change to every.
No.
They change to every
No,
single.
no, the other light.
The other lights.
The lamp.
Oh, this. It's not plugged in. Let me plug it in. Let me plug this bad boy in. Okay, hang on. I'll be right back, stream. Y'all, I was messing with my computer the other day and shocked myself. It was so funny. Okay, so are you ready? So here's the light bulb. Can you see it? And it's just like this is black felt, and then it's like, so you're thinking, oh, it's just a prop light bulb, but due to the laws of physics, you can do stuff like that, and it lights up and it hovers. Isn't that cool?
Yeah, hold on, Reagan, 1 second.
Oh, okay. Well, I'm gonna take it down so I can redo the effect.
No, thank you. I need a large root beer, a large Sprite, and a medium Coke. And a medium Coke. Yes. No, thank you.
Have a good night, sir.
I'll just give you some ones for mine in a second.
Okay, are you ready to see the light?
We saw it.
Oh. I didn't know. You look funny. Do that again. No, Grace, do it. You look funny too. Can I take a picture?
No.
Why not?
Because I look like a rat.
No, you look good.
Megan, are you ready for the recital? Did you bring flowers?
The what?
The recital.
The recital?
We're about to give you a recital.
Me?
Yes.
On FaceTime?
Back up. Back up.
Okay.
Okay, ready?
Anyway, y'all, I have the greatest girlfriend ever. So, now that all that's done, I just got off Discord with some of my homies because there's a DLD lab. And the DLD lab, Digital Logic Design Lab, is due coming up soon. So, yeah, so that's about 1.90 ohms. 1.90 ohms, and then the capacitor's not working. So this is a lie. Let me just real quick Google how to, whoa, am I lagging? Am I lagging? No, I'm not lagging. But, let me just quick Google how to measure capacitance with multimeter. Yeah, 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 yeah. Oh, okay. It needs to be removed from the circuit. I'm on flute. Oh yeah, I do have capacitance measure mode. It's just not being right, but it's the probes are in the right place. I don't know what I'm doing wrong. I don't know what I'm doing wrong. I don't know what I'm doing wrong. Well, what if I switch this? Okay, what's it say? Ensure all power to the circuit is off. What's happening? What's the capacitance of my fingers? Nothing. I was beeping it. I hope that doesn't mess it up. What's the capacitance of my headphones? Nothing. I farted. Okay, sorry. I'm very hyper because this is almost done and I'm so happy I can finally play video games. Using your digital multimeter DMM to ensure all the power to the circuit is off. If the capacitor is used in the AC circuit, set the multimeter to AC voltage. If it's a DC voltage, okay, well, it ain't AC. So, that's cool. To turn the dial to the capacitor measurement mode, which is that little symbol. So look, I have that symbol on here. You see that? It's hard to see, but yeah, it's that symbol, exactly. The symbol often shares a spot with another function. In addition to the dial adjustment, a function button usually needs to be pressed to activate a measurement. Oh. I don't know what the function button is, so let's just press some buttons. Oh! Found it! Yeah, bro, this hoe is 872 nanofarads. Bro, that's why it's messed up, because my capacitor lied. That's good. That's great. So now I'm going to have to go get an extra set of hands. So I'm going to take all this stuff to another room, go get an extra set of hands to help me, and I'll be right back. In a flash. Okay, I'm kind of back, stream. I'm kind of sort of back. Not really, because I have to go potty. So I'm going to the potty. Alright, I'm sort of back. Got my head fit. Got my headset on. My headset. Echo! Woo! I heard an echo for a second. Not gonna lie, but it might just be because I was screaming and yelling and blah 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 blah. Shall it work? It shan't. Okay, so my camera's not working, which is okay. Because am I still live? I am still live, but it says AFK. So for right now, I need to exit out of Ivy Cam. And now I need to do this. And then aha, we're in. And now I can just put it back where it belongs. There we go. That's where it belongs, sort of. Okay, cool. So now I do have, well, gotta put them on the computer, and that means I have to airdrop them from here. So we're going away for a second. Let's see. What are we gonna do? We're gonna go here. We're gonna select those two. Airdrop into the Mac. So, I do have news, by the way. And it's that the micro capacity... Oh, I already told you. Never mind. I already told the story. I accidentally deleted a funny picture of my girlfriend, so I have to go back and get it. Okay, cool. So now, I've got them on here. I can go back to Ivy Cam and switch it around. So now I'm gonna go here. I got my airdrop there, and I'm going to go to OneDrive, Circuits One Labs, Lab 7, and then just drag these bad boys in there. Are you serious? I got an ad on Ivy Cam? That's insane. Okay, there. Now we're back. So, yeah, so those two are in there. They're being uploaded. I was uploading both of them. So, they're about... So, typically this would take 1 second, but you can see how hard my bandwidth is getting hit with this stream going on. But, hey, yo, it ain't that bad. Alright, cool. So, they're in there. We can close out. And then resume the stream on there. And now I can switch this around. And I can come around here. And I can set that right up there. What time is it? Oh, it's only 11:09 and we're basically done with this. Like, literally, we're at the last step. And there's no other, like, hand calculations that I need to be doing, so that's good. Let's go here and I'm gonna download these two. Hanging Out West. Slinging, bag it out with, hanging out with, go metallic knife, I can shank you out with. I just put my drum on a no-kill tech I just put my blum in the boo boo baby da boo. I used to hop out the back of a bus, now I hop off of a jet. Why is this spinning? Microsoft Word sucks with this. Not gonna lie. Used to say what I love, but I'm love. Now I'm just slanging and speak. I'm in the now I'm just over you. I'm in a game, and a game, and a game, and a game. Hey, shawty, what you wanna suck on the tip? I go buddies, and nobody suck on the lip. Okay, what figure is this? Figure 9, so this is figure 10. Capacitor measurements, capacitance measurement left and interestingly, the capacitor is slightly lower than 1 microfarad, measuring at 882 nanofarad, and the resistors since the tolerance makes the actual measurements, the actual values, I guess, lower than documented, the actual time constant is. So now, gotta go get my towel, wherever my towel may be. It's way up here. Tau is equal to RC, which is equal to 882 times 10. Or let's do 1.995 times 10 to the 1, 2, 3. So 10 to the third. Let's do it like this. $885 times 10 to the negative, and we can get rid of this. What is the nano? -9, and then that makes, like, if nano is -9 and then you go back 3, that's 1,000. Yeah. Just Google this. Just put a cap. .00 1765, so let's just say 177 seconds, or tens, hundreds, thousands, 1.77 ms. Strangely, this is this value of the time constant is a little bit closer to the one found by measuring the oscilloscope plot window. I guess that's all I need to say. How else do I conclude this? Well, I could just have a conclusion. I also just got a Snapchat. Oh, I need to read that. Oh, my phone just dropped.
Weed. Weed. Spreadsheet, which is weed. Not that way.
Weedo.
Which is weed.
I wish I could show you him. He's a cute dog. Him's so cute. But so nasty. Oh.
Why? Who's that straw?
Let my man drink. Him's a good boy. Okay, sorry. I'm just texting. I need a conclusion. Let's put this back up where it belongs. So what kind of conclusion? In this lab, we investigated the transient response of an RC circuit. I'm going into hardcore mode of an RC circuit. A simple RC circuit was constructed and a square wave pulse was generated as the input. The time constant tau equals RC. I need that. We also discovered that the frequency. Oh, this went down because of Snapchat, probably. Yeah, it did. It went down a little bit. There we goes. We also discovered that the frequency of the input pulse must be such a must be at a certain value. Cannot be too fast, otherwise the capacitor won't have time to charge and discharge fully within a pulse cycle. It takes 5 tau seconds to fully charge / discharge. So the pulse length must be that time or less or more. Calculated time constant varied from the measured time constant, but the tolerances of the devices made to added error in the measured value. The tolerance, the actual resistance and actual resistance and capacitance was measured to reveal the actual time constant of the devices used in this experiment. Period. And that's on period T. Capacitance in this experiment. Period. Cool. This is looking like a good report. Now, what format did I upload it in? That's the question. So we'll go to labs, we'll go to my grades, and you're about to see my grades. Oh no, let me... whatever, I really don't care. Lab 5... Oh, lab 6, I got a 90 on. Table 1, missing units for voltage and power, and the results in discussion show a plot of power versus resistance and comment on it. Okay, well, anyway, so let me find my lab 6, and it was a .docx, so I uploaded it as the docx. So now I can go here, and then I can click content, and I'm ready to publish this. Like, I don't see no typos. Well, just making sure there's no red underlines and whatnot. But, yeah. I guess that's good with me. It's 1,000 words. That's a lot. I'm gonna submit it because I'm tired. I know it's 11:24 and I could wait a little bit, but no, I'm gonna turn it in now. Get it done early. You know, Lab 7 report open. Okay, it's in use, so I have to close it. And now I can open it. There we go. Lab 7 report. Submit. And I have to wait till it uploads, and I'm good to go. And then after this, we're going to celebrate. There it is. It's gone. Submission received on this computer. There it is. I can archive this and delete it from here. Cool. It's done, guys. I did it. And I have one more lab to go tomorrow, and I'm going to live stream that. But for now, I'm thinking that this is good. This is great. So, yeah, that's pretty much all I've got for right now. For right now, let me stay on the stream, though. I'm going to close out of this waveforms. I'm going to save it, actually. I'm going to save it into OneDrive. I'm going to clean up everything so I have a clear mind for gaming. And I'm going to call this just Lab 07. Save it, exit, and then unplug it from here. So analog discovery is gone, and then these pins are all going to need to come out because I don't want to lose them. And that looks like all of the pins that I can see, plus two more, two more here. So there's 1, 2, 3, 4, 5, 6. Perfect. That's the good number of them. And then I put this in the bottom of my thing right there. The capacitor is going to go right down in there. All safe and sound. The resistors and this thing. Breadboard goes here. This thing is going to go right here. This jumper cable. And then these thingamabobbers are going to go in here. The little pins go in here. My brain is on fire right now. Like, oh my gosh, I can't believe I did all that. Like, I mean, I do it all the time, but like, I don't know, I'm just going wild. And then here's my little 1 kilo ohm resistor bag. And then I just throw them all in here. So I know that those are the 1K. Because I hate looking at the color codes. Like, I've memorized some of them because I just use them all the time. But I'm not going to look at the color codes. I just put them in separate bags and grab them, and I know that they're right. And now I can close that up. Actually, the digital multimeter, though, I don't know where that was at. Oh, it's placed down right here. I need to clear this thing, this notebook, the DMM, digital multimeter. It's going to go here. I can save my coffee, but I'll put that in the fridge once the live stream ends. And then I can shut my circuits box, close it up, slide it underneath the desk. Got my pen, my Neosporin, for whatever reason, it's still there. And then this is organized. There we go. And am I still connected? Yep. Okay, perfect. That's it, guys. I did it. I want to celebrate, so I'm going to do so. Now, certain people are sleeping right now, so I would normally play really loud rap music, and then I would set my lights to flash like that, and then I'd turn out the lights, and I'd just party. Woo, 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 woo. Let's go, Mo. I got hoes calling a young Nimbus phone. But anyway, instead, I'm gonna put these on red for gamer. I'm gonna go ahead and turn this back on so I can say my goodbyes, and that's it. Goodbye, guys. Thanks for watching. I'll see you next time. Peace. But anyway, instead, I'm gonna put these on red for gamer. I'm gonna go ahead and turn this back on so I can say my goodbyes, and that's it. Goodbye, guys. Thanks for watching.